Hi, everyone. It's really nice to be here, and thank you so much for everyone for coming. Today, we want to introduce to you a domain-specific large language model called MALENA, built by the International Finance Corporation. And we would like to share with you our experience of using Databricks GPU compute and GPU model serving, first of all, for building and also serving MALENA. My name is Blaise Anwidi, and my colleagues and I, Jonathan, we work for the International Finance Corporation, the IFC. And IFC is part of the World Bank Group. And this part of the World Bank Group is focused on making investment in private sector. And this past year, we invested almost $44 billion in private company in emerging market. Part of our mandate when we make those investments is to ensure the client business impact in terms of sustainability. We specifically track the client, worker safety issues or pollution prevention method, and how the company that we're investing in are engaging with stakeholders, for instance. But why the IFC is doing data science? Why IFC is building a tool like MALENA? One of the reasons is that I talk about the $44 billion investment. This means that our specialists need to spend a lot of time in reviewing a lot of text document, right? And they have, in average, 10 to 20 documents to review per week. And they typically have just a few hours sometimes to make it happen. This document review process is very time-consuming, and the primary purpose of building tools like MALENA was to help us speed up this due diligence process. Why IFC? Why are we uniquely placed to build an AI tool like MALENA? First, being in business for nearly 70 years means that IFC has collected a lot of ESG and sustainability data through project execution, through operations. And the second is our ESG domain expertise. IFC has one of the largest ESG team in the world. It's 200 plus ESG experts. And we combine those two important assets to accelerate the way of building ESG machine learning algorithm. And this allows us to understand the AI tools that we're building to understand more than 1,000 ESG topics. And also, in addition to the time-saving motivation for us to build a tool like MALENA, we really think that AI tool can help us, first of all, bridge the sustainability gap between on ESG data first. And second, we think that MALENA can help us also fill the funding gap to meeting the sustainability development goal, which is $5 trillion annually. With that, I want us to take a short break and watch a very short video to see how MALENA is helping to advance the sustainable investment.
Embracing the power of big data and artificial intelligence, the International Finance Corporation presents MALENA, an innovative machine learning ESG analyst to transform sustainable investing. MALENA is an artificial intelligence-powered solution built by IFC to identify meaningful environmental, social, and governance insights from text, almost in real time, and in turn, increase efficiency, boost productivity, and build investor confidence. Using natural language processing, MALENA can read sentences and identify more than 1,000 ESG risk terms. MALENA then rapidly assigns positive, negative, or neutral sentiment to each risk term based on its context. Users can upload documents to the MALENA web portal for MALENA to read and identify ESG topics, such as how much water a company used in its operations, or the number of women members on a company's board, or any risks a company may have posed to the health of communities in the last year. MALENA reveals the location of ESG terms within a document, in addition to highlighting the corresponding sentiment in which these ESG phrases appear in a sentence. For instance, MALENA determines whether words related to water appear positively in a sentence like total water consumption has decreased, or negatively in a sentence like flooding is a dominant hazard for the company's assets. As a result, users are aided in swiftly identifying a company's strengths, weaknesses, and locating additional pertinent information. MALENA's strengths are speed and accuracy. MALENA can read a staggering 19,000 sentences per minute with an impressive 91% accuracy. MALENA, leveraging the power of data and AI for sustainable investing.
All right. I hope you enjoyed the video. If you have to keep two words in mind, will be the MALENA speed and accuracy. Thanks to GPU model serving for the speed, and thanks to our domain expertise for the high quality model with 91% accuracy. How did we make it happen? What's the infrastructure set up for that? As I explained, most of the document that we use to review are text document, and those data, unstructured data, are coming from, first of all, our project documentation. Those are proprietary data that our specialists have to produce, and we use those data for model training also, and also for model at the inference stage. The second type of data that we are ingesting every day is the company public disclosure. Could be annual reports, statutory report, bond practices, and so on. And the last component are ESG news report, and we're ingesting 1,000 per day to feed to the algorithm in terms of model training again, and also inferencing. The data are stored using Azure Data Lake. As you can see, there is an interesting mounting mechanism between Azure Data Lake and Data Factory with Databricks. This is super helpful to us because we were able to perform data engineering activities such as name entity recognition, document deduplication. It's super helpful to data scientists like us. As you may expect, we're not only doing data engineering with Databricks. The most exciting part is fine-tuning large language model. And MALENA is a version of the fine-tuned large language model. We started in 2020 with Google BERT, and then we transitioned to Roberta. And more recently, we are experimenting a lot with open source model like Mistral, Llama 2, Llama 3, DBRX. And one interesting component in Databricks is also MLflow. All the fine-tuned models are the model weight, artifacts, the model metrics, performance metrics are saved in model registry using MLflow. And this is, again, super useful because you're doing everything in the same workspace. And then once we train the model, save on model registry, now it's come to the serving. And so far, we have been using 3 approaches to serve the model. The first one is the batch inference using Jupyter Notebook with workflow, Databricks workflows, of course. To every night, midnight, we have an incremental job running in the backend to use the trained model and run inference on it. In the middle, the second option, we have implemented since long back a serverless Azure function as a way to provide to the end user a real-time experience. They can then upload, they don't need to wait for the midnight job. They can instantly upload document into the MALENA platform, and the model will be able to give them the results almost in real time. And the last serving option, which is the the main topic of this talk is the GPU model serving. We have started exploring that because we wanted to be able to even improve the user experience, right? So everyone wants to have the response as quick as possible. And we think that the GPU model serving is the best option for us to be able to serve MALENA efficiently and quickly. And my colleague Jonathan will tell you more about how the GPU serving is working and how performant it is. Right. So, yeah, what's this infrastructure setup allow us to achieve so far? We were able to deploy a domain-specific model. We put it into production since January 2022. So, which is EEG sentiment analysis model. It's specific to EEG and it's performing very well, like we explained. It's 91% accuracy. We were also able to expand the model to do translation, for instance, to perform name entity recognition. It's super useful because sometimes the news and the unstructured document are not mapped to specific entities, right? You need to be able to tag a specific news article to a specific entity. And name entity recognition has been super useful to us. And more recently, we have been experimenting a lot with RAG application, and we were able even to get some very high-level accuracy with question answering for a specific beta tester questionnaire. They have a set of questions, and they want to use Mistral or Llama 2 or 3 to answer to those questions. And of course, the one last thing that we're trying right now is ESG-specific text generation, right? So, right, what's the current state of MALENA? To be clear, the tool that you have seen through the video is not like it's not at the MVP stage or prototyping phase. We put it into production within IFC in January 2022. We have used MALENA to run inference on over 250,000 documents. We were able to detect millions of risk terms, means interesting insight for our business. We were able to create more than 20,000 companies profile that cover 806 countries and 26 sectors. Like I mentioned before, we expanded the algorithm to understand the World Bank Group language and also language like Korean and Turkish. This is the internal version. Our external rollout strategy is very clear. We would like to, and we have released a public good version of MALENA. Meaning that everyone, you can try and give us feedback, can access to the MALENA platform, and you can see the URL can access the web interface and upload document, and you can instantly get feedback from the application. This is free. You won't be able to see IFC data. This formula is like bring your own data. You have your company report, sustainability report, and you want to get some insight, you can quickly upload it to it. And the last component is the API. It's the B2B API version that we released on end of March this year. And this says for companies, big banks, financial development institutions, private companies, and so on, with some specific requirement, because they have a data privacy requirement. They want to be able to use the algorithm to process the data at scale, and the API is for that. And for the API, this kind of motivates us and pushes us to experiment a lot with GPU model serving as an alternative to the serverless Azure implementation. And Yeah, that's it for me, and I will hand over to Jonathan. He will share with you our experience of, in terms of comparing the serverless Azure function. We may have some benefit there to GPU or model serving. Okay. Over to you, Jonathan.
Yeah, thank you, boys. Thank you very much, Blaise. Hi, everybody. Thanks for your attention. So, as Blaise has explained, we've been using serverless Azure Functions to perform machine learning inference. And when we delivered this B2B API, we had the opportunity to evaluate some alternatives. Since we're doing all our training in Databricks and we're using the model registry, Databricks model serving was a natural choice to try out. And we expected GPUs to be more performant than the CPUs in Azure Functions. And shortly, we'll talk about how much more performant they are. Now, on this slide, we have a breakdown of exactly what the B2B application does when someone uploads a document. What kind of analysis do we do? In our case, the workload can take several minutes. Unlike a chatbot or a classifier that can answer in a few seconds, these documents can be very complicated. They can be hundreds of pages long, and we have several stages of analysis to perform on them. All our models are in English, so first, if necessary, we translate the document from another language like French or Spanish into English. And we use a separate Azure service for that, so that has no CPU implication, but we have to wait for it, so I/O intensive. And then the biggest pre-processing work is optical character recognition, or OCR. So a lot of our documents are scanned, and we need the position of each word on the page to render our results in the UI. And we do other pre-processing, like splitting the document into pages and paragraphs. And all of this, again, is very CPU intensive. And then I wrote term detection. That's mapping our ESG taxonomy to the document. So we find relevant ESG risk terms like child labor or air pollution. And for that, we may also use an external service. And finally, the heavy work is the sentiment analysis itself, which is, of course, very CPU intensive or GPU intensive if we have one. Then we can aggregate and return the results. So while all this analysis is running, we allow the user to poll for the job status so they can query the results when they're ready. And when we're done, the results look like that. So we have targeted sentiment analysis on specific terms in the document, risk terms mapped to our ESG taxonomy. Our users can see the key ESG risks highlighted in context in their documents or aggregated based on our taxonomy. All right, now we'll talk about the testing that we've done for GPU serving. So we're interested in load testing, we're interested in latency and throughput, and scale out behavior of our solution. So we have some scenarios that we wanted to test. Our API usage is bursty, so a client may upload 50 or more documents all of a sudden in a batch. So we're very interested in, again, scale out behavior. So first we'll focus on the most expensive part of the computation, the sentiment analysis. And for that, we can look at the Databricks model serving endpoint in isolation. So for instance, we have a scenario where we have 1 request per second and 25 sentences in each request. And that's somewhat comparable to real-world load. And then we'll look at overall system behavior. So that's including the pre-processing and the job state management. And for that, we'll need to upload full PDF documents. And 30 documents in 30 seconds will be sufficient to give our experimental setup a workout, although we have more resources in production. All right, so I'll start going through some of our experimental results. So this is a latency and scaling test we did for the sentiment analysis model in isolation. Each color here represents a type of compute offered by Databricks model serving. And we can focus on the blue dots first. That's CPU small, the smallest type of compute. And the difference between the small, medium, and large is just the number of instances that they scale out to. That's 4, 16, and 64 respectively. The x-axis here is the request start time, and the y-axis is the latency. And each of these dots is one request. So as you move to the right on this graph along the time of the experiment, you can see how the latency changed. So again, focusing on blue first, that's CPU small. At the far left, at the beginning of the experiment, the blue dots are low, the latency is under 20 seconds. But it slowly steps up as the model falls behind the incoming requests until finally a little past 30 seconds, the requests start timing out. And the blue dots are in clusters of 4 because again, we're running this model on 4 CPU small instances, and that number does not scale out for this type of compute. Now, CPU medium is the yellow color. So again, we just ran the same experiment with a higher compute level. And in this case, the latency increases much the same as CPU small, but instead of beginning to time out, the endpoint scales out and the latency drops back down. This is the kind of scaling behavior that we wanted to study. As the workload overwhelms the compute scales out, latency drops down. And you can see the same behavior with the red color, which is CPU large. And finally, the green color is GPU small. The GPU is much more efficient, so the latency stays so low that actually there's no need for it to scale. So there was no point in testing GPU medium or large for this scenario. 25 sentences per second is 1,500 sentences per minute. So you can see that if we scale out the GPU endpoint, we can match the 19,000 sentences per minute that Blaise mentioned before without much trouble. You can note that the CPU medium endpoint scaled out in half a minute, and the CPU large endpoint took a bit longer. I don't think we ever saw the inputs take more than about 2 minutes to scale under heavy load. So they're very responsive. So congratulations to the Databricks team for that. We struggled with scale out time when we were using pure Azure Functions. Caveat though, we don't have numbers for GPU scale out here. All right. Sorry, please go ahead. Okay, yeah, at the end, we'll take questions. Thanks. Please. All right. So as I mentioned before, the previous measurements were evaluating the sentiment analysis model in isolation, but our application performs a lot of pre-processing on our PDF document inputs. So how much does Databricks model serving improve the overall system performance? This is more relevant for us. So this is a comparison of 2 test runs with a burst of 30 documents on an Azure Function only system and a hybrid Azure Function and Databricks serving system. On top, a document is uploaded into an Azure Function. It's processed in 1 of 3 instances, and then the results are returned without any external input. And on the bottom, the document is uploaded to the Azure Function. It's pre-processed in 1 instance, and then the pre-processed data is handed to Databricks model serving for the actual model inference. The compute choices might seem arbitrary now. I have more details on the next slide for that. But anyway, each horizontal line here represents a request for a PDF document to be analyzed. And the dashed line is the period where the job is queued, and then the solid line is the period where the job begins to be running. The main observation here is that Databricks model serving significantly improved throughput. I'm sorry for the changing unit. We switched from sentences to pages per minute, but it turns out our testing team prefers to count pages than sentences, which makes sense. The Azure function in the lower system is a bottleneck since it needs to manage the job state and do pre-processing all by itself to keep the GPU endpoint busy. We're still experimenting with the right cocktail of concurrency here, but this comparison is interesting because the price of these two systems is similar, as we'll see in a moment. But these systems are very sensitive to any concurrency settings, like the number of processes running, or here, the number of instances. All right. Now we'll summarize the quantitative performance of our different Databricks and Azure model serving solutions for our workloads. I'd like to emphasize that these numbers are just for our specific test scenarios and our configuration. And I'd like to encourage other teams to do their own testing and check your own pricing too, because that varies. You can see the price of the two systems we compared on the last slide are about the same. So for another nickel per hour, we gained almost 40% more throughput and improved latency. Like I said before, a lot of sensitivity to the concurrency settings. So we can get an even bigger throughput win, but at the cost of latency. The throughput is predictably a strong supporter of GPU serving. And we'd like to raise throughput as high as possible without compromising on latency for our critical scenarios. GPU model serving was the best option by these criteria. We can scale GPU serving the same way we can scale CPU serving. So these costs rise linearly and on demand for higher workloads. So in summary, we found that even with a heavy pre-processing and a relatively light model, GPU serving is an economical and efficient option. All right. Now I'd like to review our qualitative experience with these different model serving solutions while we ran these experiments. We shouldn't compare Azure Functions to Databricks model serving directly. It's a bit apples and oranges because they cater to different use cases. But this review may help you decide when to try out model serving. Implementation complexity. If your use case is simple input and output, and especially if you're already using Databricks for training, you're already using the model registry, Databricks model serving is a great solution, and you can expect to get it working quickly. If you have a more complicated use case, like in our case, a long-running job with status updates, Databricks model serving may still be a great option, but you likely need more infrastructure for orchestration and state management, like Databricks workflows maybe, or in our case, durable Azure Functions. Model serving will not get you the whole way there. Keep in mind both Azure Functions and Databricks cluster startup time, so you may need to use pooling for acceptable cold latency. All right. Azure Functions are a great general platform. They can handle a wide variety of API designs. They can handle multi-part form data inputs, which we needed, and we integrated them with our DevOps easily. But they're not specifically designed for machine learning, and we did face challenges with their scaling and performance. Azure Durable Functions turned out to support our use case really well because they support state and job status checks natively, but they're still not perfectly tailored to machine learning. We should also say Azure offers a lot of control over the scaling rules. For example, you can add a rule specifying that the system will scale out when CPU hits a certain % utilization. Azure serverless options also have more logging functionality. To be fair, once your machine learning model is deployed, you shouldn't need to do much debugging, but reality is cruel. They are more general, so in particular, durable functions are a more versatile solution. Databricks shines when you can take advantage of the model registry and MLOps integration, when you need on-demand scaling, and most of all, when you need GPUs for high throughput. All right, now what is the future of MALENA? I'll run all that. In terms of AI research, we'd like to deploy more retrieval augmented generation or RAG applications using Databricks model serving. We've already done several proof of concepts and one-off exercises using RAG, and we're going to continue to integrate it into the MALENA application. Optimized model serving, the foundation models in Databricks, has been really helpful for this. Vector database search with Unity catalog is there to support RAG applications and other semantic search work. We'd like to integrate the GPU model serving, as we've presented today, for complex document processing because it's more efficient. We'd like users to benefit from fast responses, even when they upload many documents at once. We need long-running job status updates and checks for our full model serving solution. And we implemented this with Azure, as you've seen, but we'd like to try out a pure Databricks solution as well, maybe using workflows. And fine-tuning ESG domain LLMs is kind of what we're all about. This is very exciting. So just like we fine-tuned our BERT or Roberta models, we're beginning to fine-tune the cutting-edge large language models as well, like Mistral, Llama 3, and DBRX. On the data automation side, we've been collecting feedback on our inferences, and we'd like to close the loop of training and redeploying models. All right, so I'd like to share 3 takeaways. So first, we can demonstrate with GPU compute and model serving that we can build a very high-quality domain-specific model with 91% accuracy and serve very efficiently, processing 19,000 sentences per minute. And this has been very helpful to the IFC in terms of time saved during project due diligence. Second, we encourage teams to try out Databricks model serving with GPUs and compare their cost and performance for their machine learning applications. And third, MALENA is much more than a technological advancement. It's a catalyst for sustainable investment. And we believe MALENA could play a crucial role in closing the funding gap to meet the UN Sustainable Development Goals. That's all I have. Thank you, everyone.